the project work is an important part of S281. And therefore, I want to give you some assistance with it by walking through the observational part of one of the projects, the one in which you measure the difference in the length of the sidereal day, as measured by the stars, and the mean solar day, as measured by your watch. So, what's to do? Well, before you start any project, you should make sure that you first read the project book and study the appropriate project sheet. If you haven't already done so, then please do so now before watching the rest of this video sequence. Well, from the project sheet, you can see that what you have to do is to measure the time at which a star appears to move behind a building, so it's blocked from your view. This is because of the rotation of the Earth. You then repeat the measurement of this time on at least one subsequent night, and preferably on several nights, and then you analyze your measurements. Now, I've chosen the star Rigel as the star to observe. And the reason that I've chosen Rigel is that it's comparatively bright, easy to find, and is well placed in the evening sky currently. To check that it's well placed, I'm going to use the planisphere. So let's set the date, which is the 10th of February, against the time, which is 7 in the evening. And I can see that, indeed, Rigel is well placed. It's about a third of the way from the horizon to the zenith. As the evening progresses, Rigel moves westwards, and a few hours later it'll be about there. I can see what time that is. It's a little after 10 in the evening. Still well placed. So let's go. Well, this is my chosen observing site, and note that I'm well wrapped up against the February evening weather. Note also that I've brought quite a few things with me. First of all, there's the project sheet in there. I've also brought a torch, of course, and particularly my project book, something to write with, and most important, my watch, which I've set accurately before I came out. Now, my chosen vantage point is this post here. This is where I'll make my observations from, and that building over there, the edge of the BBC Open University building, is going to be the reference edge behind which Rigel will pass. Well, actually, it's not Rigel at all. It's cloudy, and so instead of Rigel, we're having to use an artificial star, a car headlamp bulb. It will do well enough as a simulation. Well, now I better start writing things down in the project notebook. First of all, today's date, the 10th of February, and then a sketch of my observation site. Plus the fact that I'm using Rigel and the building over there and so on. But most important of all, details of exactly where I'm going to place my eye. And what I'm going to do is to lean against this post, like this, and use my left eye to make the observations. And it is important that I write all that detail down. Well, let's get our star moving, and then I just have to wait and watch. Well, Rigel is approaching the reference edge. Now, what is it that I'm expecting to see? Well, Rigel won't actually just suddenly go out of view, and the main reason for that is that I can't keep my head perfectly still. So the effect is that Rigel sort of bobbles in and out of view. And what I'm going to do is to take the time when it's as often in view as it is out of view. Okay, let's do it. Right, here comes our artificial Rigel up to the reference edge. There it is now bobbling. Of course, the real thing would be rather different from this. There we are, that's about half in, half out, and now I want to record the time at which this is happening. Right, there we are. If I record the time to the nearest half minute either way, that'll be perfectly adequate. Well, that's it for tonight. What I want to do now is to come back here on at least one further night, and preferably on several further nights. I will then have all the data I require. The analysis of the data, this is described in the project sheet and also in the project book. And when you've got your measurements and analyzed your data, then you'll have your value of the difference between the length of the sidereal day and the mean solar day. Now, Now, if you have any difficulty in understanding how the stars move and why there is the difference between these two day lengths, then you should certainly watch the next part of this videotape.
Imagine that this represents the Earth's globe. The vertical axis passes through the poles. This ring represents the equator. What would we see in the sky from this particular point on the Earth's surface in the northern hemisphere? From any such point, we can look upwards towards the local zenith, vertically above us. 90 degrees from our zenith, we have the horizontal plane that touches the Earth at the point. This plane stretches away to the horizon and divides the sky into the half that we can see, which lies above the plane, and the half that we can't see, which lies below it. To see what happens when the Earth rotates, we need some reference direction that remains fixed among the stars. Our reference direction goes from the center of the Earth, through the Earth's equator, and on outwards. Thus, as the Earth rotates on its polar axis, this reference direction remains fixed. Even though the reference direction is from the center of the Earth, the stars are so distant that this direction seems fixed among the stars even from the surface of the rotating Earth. Thus, if we zoom outwards towards the stars, the dimensions of the Earth soon shrink virtually to a point. To keep track of our earthbound coordinates, let's extend the rotation axis, the Earth's equator, the reference direction, the horizontal plane that shows which half of the sky we can see. To include some stars, I need to plot their directions on an imaginary sphere, the celestial sphere. The projection of the Earth's rotation axis intersects the celestial sphere at the celestial poles, and the projection of the Earth's equator forms the celestial equator. We can show the reference direction as a point A on the sphere, and in fact, our choice of reference direction means that this is the first point of Aries. Now let's add the directions to three real bright stars. North to the pole star in a direction very near the north celestial pole, then to Betelgeuse in a direction near to the celestial equator, and finally, below our horizon, south to Canopus. Again, we can show these directions as points on the sphere. Note that from our point of observation, the pole star and Betelgeuse are above the plane, so are visible, provided of course that the skies are dark and clear. Canopus is below the plane, so is not visible. Now watch what happens to our view of the stars as the Earth rotates. Let's hold it here. The pole star is still above the plane, so is still visible to us. Whereas Betelgeuse is just about to become invisible, it is setting. Canopus remains below the plane, so remains invisible. The Earth, of course, continues to rotate, but let's stop it once more. Betelgeuse is now rising to become visible again, whereas Canopus remains invisible and the pole star visible. Indeed, from our viewpoint high in the northern hemisphere, as our horizon rotates around the celestial sphere, the pole star is always visible in a clear dark sky, whereas Canopus is always invisible. What is our view of these stars from a different point of observation on the Earth? For a point just south of the Earth's equator, this is the horizontal plane that determines which half of the sky we can see at any moment. And this is the view from outside the celestial sphere. With our horizon in this position, the pole star is below the horizon, but Betelgeuse and Canopus are above it. Thus, from our more southerly point of observation, Canopus can now be seen. Some hours later, all three stars are below the horizon. Indeed, the pole star is now never visible. So, what we see depends on where we are on the Earth's surface. This is a long time exposure from a point on the Earth's surface, thus recording the apparent paths of the stars across the sky. You should now be able to understand this photograph. Test yourself. For example, the stars appear to rotate about a fixed point in the sky. In what direction does that point lie? It lies in the direction of a celestial pole. Replay the rotation animations if you don't understand this. In fact, this photograph was obtained in the southern hemisphere, so the fixed point is the south celestial pole. To conclude this sequence, let's consider briefly the difference between the solar and sidereal days. The sidereal day is the period for one complete rotation of the Earth with respect to the distant stars. The solar day is the period of one complete rotation with respect to the Sun, and it is different because of the orbital motion of the Earth around the Sun. This makes the direction to the Sun appear to move around the celestial sphere once a year. And here is our rotating horizon, rotating as the Earth rotates. Thus, the Earth has to rotate a bit further to catch up the Sun, and so the solar day is a bit longer than the sidereal day. In your project work, you should obtain a reasonable value for the difference in length between the solar and sidereal days. More broadly, you will gain direct experience of many aspects of the apparent motions of the sky.